Hi, my name is Michał Dąbrowski. I'm from DaftMobile, and today I'm super excited to talk to you about multiplayer games, different approaches basically to coding in multiplayer games. What are the advantages, what are the disadvantages of certain architecture approaches, and how to utilize them in your next multiplayer game. But first, a few words about myself. As I've said, I'm from DaftMobile. We are a gaming company focused on mobile games here in Warsaw, as well as mobile apps on the App Store as a part of Daft Code Group. And one of our projects is Elympics, which is a universal tool to create that allows you to create multiplayer games. And I'm super excited to talk about that as well. I'll come back to Olympics later in this presentation. First, let's take a step back, huge step back actually, to gaming history, I would say. I'm sure most of you are familiar with this example. That's basically, that's Pong. It's actually the first video game ever implemented, I believe. Anyway, when we look at from the coder's perspective, again, at the architecture of such games as such old games, we see a block of code that's there, and basically everything had to be created from scratch, from the displaying engine to physics, ball bouncing, and so on. And during those years, during years of improving of the video game industry, we developers, we like to make our lives easier, of course, and we like to automate and not to repeat ourselves. And in that spirit, game engines were born. So game engines, for example, like Unity or like Unreal or like Godot, they take all the tasks that had to be implemented, done over and over again in older games, and they separate that into an easy-to-use available library, available tool. So, for example, all those things like physics engine, threading, collision detection, memory management, and so on, animation, of course, rendering pipeline, GPU abstraction, and so on. All those things have been separated to game engines so that we as developers, as game studios, can focus on what's really important and what's really unique to our games, which is of course our game design. Because our games use all those features of a specific game engine, and we depend on them, and we depend on what they tell us. For example, collision detection, we run some event when a collision happens. That's common and that's game engine dependent. And that's why it's not really possible anymore to talk about our game logic with separation of the game engine, most of the time. I just wanted to acknowledge that, and it will be important later in the video, in this presentation. But let's take a step back and think about what we have to create when we want to, what do we have to do when we want to create a multiplayer game. So obviously we'll have, instead of just one client, we have now two in the simplest possible example, and we have to somehow connect them by sending messages, by synchronizing something in the game world, or just sending plain messages. And the perfect scenario that's a utopian scenario, which is not possible, is a networking layer. It sounds great, and the networking layer would do everything for us, but because of connections between our game logic and the game engine, it's not possible to abstract the communication just to a layer that's independent of the game engine or independent of the game code. And also, do I need a server? That's a good question. For some multiplayer games you have to have a server, for some you don't. I'll also be exploring that later in this video. Okay, again, a step back, and let's think about it. Even why are we talking about this? Of course, when you try to create a multiplayer game, you're gonna need some netcode, whether you want it or not, whether you like it or not. And it's important that you understand which one are you going for, because sometimes when you're late in the development process, it's too late to change. So it's really important that you understand all the advantages and disadvantages of various networking methods, synchronization methods, so that you make the best decision for your game and for your design. Because if you don't, and late in the development process you realize that you've made a mistake with architecture choice, it could be too late. And just like it would be too late to change the game engine from Unity to Unreal, for example. Okay, and with that, we can start with our first basic networking approach, which is the easiest that comes to mind, which is obviously peer-to-peer. So the most simple possible idea, you have two clients, and in the simple case, two clients, and you connect them. So sending messages from one to another. And obviously, you'll need to discover players on the network, on the local network. You have to establish this local connection, direct connection between them, and you can send arbitrary messages. There is our first problem with that implementation right here, because as the number of clients grows, we have more and more messages to send, and it's more and more difficult to synchronize between those players. But that's just one of the problems. So in peer-to-peer, the simplest possible implementation, there is no server needed, so no server architecture. You don't have to deploy anything. You basically have to manually discover players on the local network, and you have to then you're basically free to, when you start the game, you're free to send whatever you want between them. But if your game design is strictly local, so that you have to be in the same room to play it, it's perfectly viable. So for example, there are many games created with peer-to-peer, one of which I would like to mention is Space Team. Their game design is heavily focused on playing in one room. It's not possible to play any other way, so it was a perfectly viable choice to choose peer-to-peer networking. But of course, some games need to be played over the internet, so we can do better, we have to do better. And to play over the internet, you need some sort of server, always. And the first idea that we're going to explore is client authoritative, which is, one way of saying it would be it's peer-to-peer but with a server, and I'll show you what I mean. You basically take the server and just use it to forward messages, and that's called client authoritative. So when new peer arrives or join the game, then they only send messages to the server, and the server responds with the state, for example. So that's the basic idea of client authoritative. So server just acts as a message relay. It just forwards messages from clients to clients. There is no custom game logic on the server, so you can reuse server for all kinds of games. They do not need any game specific logic. They're just there to host a match and forward messages between players. And in most common implementations, clients send the current state of their game object. So if I'm controlling one cube and the other player is controlling the other cube, then we basically just send our current position, and the server forwards it and synchronizes it. It's of course used in many successful games. For example, Dark Souls used this approach. And it's perfectly viable and possible to use it. And okay, let's explore the implementation now. And we'll be using a very simple example. So in this game, we have a game world which consists of 6 empty fields with numbers from 0 to 5. and one of those will be filled, so there will be one square that is shared between players, and all players can do is move that square left or right. So that's our very simple, very straightforward game logic. It's not applicable to any actual game, but it's just there to show the possibilities of any particular game engine, networking implementation. Sorry. All right. So here we have. Let's start. In these diagrams, we'll represent the server in the middle, of course clients on the left and on the right, and here we'll have time axis which will be going down. So in these diagrams I'll show you the different messages being sent from clients to servers and from servers to clients, and in client authoritative as well as all the following implementations, multiplayer implementations, clients will only be talking to the server and server will be talking to all those clients. So clients do not share any connections between each other. And let's start by, of course, we start with an initial state. So let's say our square is on position 1 and the server sends the state to each player. And let's say client 1 wants to move the square right. And of course the player pressed right arrow. The new state was applied by the game logic, and the new state is being sent to the server. The server reads it, acknowledges, okay, the square is now at position 2, and forwards that message to all other players saying, hey, the square is now at position 2. Pretty straightforward. And yeah, in these videos you'll be able to see the problems with all the networking approaches, as well as the advantages, obviously. And this game is basically another two-player game with one player controlling the blue box and the second player controlling the green box. They can move their boxes around, respective boxes around with their input, knocking some of the boxes that are there on the floor. And so let's start the video, and now you can see, let's first focus at the video on the right. So on the right we can see the green player moving and knocking some of the boxes on the floor. And that's his perspective. So on the right we can see the game from the perspective of the green player, and on the left we can see the game from the perspective of the blue player. So we can see that the game plays perfectly fine on the green player's screen, and so on the right. But on the left it's not so good, because the player only sends their current position of the green cube, and that's all the blue player receives. So he's able to apply it on the game world. So we can see all the movements of the green player. However, all the other elements of the game are not being moved in the same way, because we only send the current state of our own box and not the whole world. The game on the left, so the blue player's game, is not able to replay all those physics interactions, and so the game becomes highly undeterministic, especially in physics-based games. Here we can see basically the same thing, but laid on top of each other. So we can see a ghost of the green player on their screen and a ghost of the green player on the blue screen laid on top of one another. And the green tube is following perfectly the path from the green player's game world. However, all the boxes being hit by the green cube, all the little boxes, are desynchronized. And you could, of course, try to solve it in some way, for example, sending the whole world state and not just the green cube state, which would be viable. However, it would be viable and it would work only as long as only green player would interact with those cubes, because basically you have no central place to merge any changes. So you wouldn't be able to determine which movement, which position of cubes on the floor is correct if all the players try to send them. So now you can see that the cube, the green cube bounces and gets a rotational angular force, angular momentum from bouncing of a cube that is on the floor. And from the blue player's perspective, they don't see the actual bouncing, they just see a rotation which seems to appear out of nowhere. So that's the difference and possible difficulties with implementing client authoritative. Okay, let's go back. Let's take again a step back to our diagram here. And there is another problem that I would like to briefly touch on, which is cheaters. So in client authoritative, there's basically no central game logic, no such thing as a central game logic. And so when one player is trying to cheat and basically say, okay, right now I'm here, there is nothing that other players can do. The server just accepts it and forwards it to other players, and they have to accept it. So cheating in client authoritative. You basically can do anything, just like in peer-to-peer. You can modify the game files to give yourself OP items. There's no way to block players from performing illegal moves. So I can just say my cube is now here, and all other players have to accept it. Also you can change some properties in your game engine if you know how to connect a debugger, for example. So you can change some variables like character speed, attack, HP, and so on. For example, it was used and exploited in Dark Souls when characters would increase their HP and attack and be just impossible to defeat. And all other parties in this particular multiplayer implementation have to just accept the new state. So to sum up, client authoritative. There is no code on the server, no game code on the server. It's a very affordable server architecture because you only pay for bandwidth. There's nothing that actually runs on the server. There's no central authority on game logic and no real game history available. Also, there is no easy way to synchronize the game world, especially if players can come into interactions with common elements of the world. There is no easy way to synchronize them, and for such goals you have to create your own synchronization code, which is challenging. It's also, it's good enough for casual games, especially when you want to create just a simple game to play multiplayer, for example, in co-op games, or as I said, in casuals. But this architecture, when your game started as casual and its player want to play it competitively, there's basically no way to prevent cheaters, to fight cheaters. There's only so much you can do with client authoritative. And of course we can do better. And let's go to the third possible implementation. But before doing that, let's take an inspiration. Of course, we know the internet and we've all used internet browsers. There's this fancy protocol named HTTP. And let's take some inspiration. So how does it work? Obviously, we have a client, which is the internet browser, and we have a server. So for example, when you type google.com or daftmobile.com, why not? In your address bar, you send a request to the server, and the server delivers the response with a web page. So let's take an inspiration in that and try to create we'll call it turn-based server authoritative, You'll know why it's called turn-based in just a second. So the idea is now we thin out not the server, but we thin out the clients. So there is no logic, just like on HTTP, there's no google.com website in your browser. The server responds with the full web page contents. So server now contains the game logic. Clients just send their inputs. So for example, I want to move right, I want to jump, I want to shoot, and the server just responds with the current game state. And of course, the server needs to do that if we have no game logic on the client. The server has to do that 60 times per second, or how many the server has to do that 60 times per second in 60 FPS. And there are some games that use this approach. One of them being, for example, chess is the most sensible way to implement a game like chess, because you basically just take the action that the player wants to perform. So for example, e4, you send it to the server, and the server can respond with the new board, so saying illegal move, or with e4 applied and now it's black's turn, for example. It's also used in some turn-based game, like for example Hearthstone. And how does it work? We'll just focus on one client and server for now. Obviously, the same way that we've seen in the client authoritative example. We start with the game state, we broadcast it to all the players, and now instead of applying the input locally and sending the new state to the server, we just send the input. So we send I want to move right to the server, and the server applies it and responds with the new state. And then after we receive the state, we're able to display it. And now let's see the same thing in our example, GameCube example. So here we can see 3 games simultaneously. On the left we can see the game from the blue cube perspective. On the right we can see the game from the green cube perspective. And in the middle there is the game from the server's perspective. So what's being played on the server. And let's start. So we can see that the game is perfectly synchronized with some delays obviously, but the final game state is exactly the same on all the clients and the server. All those cubes are, it's basically being run just on the server, and it's fully deterministic. However, there's a problem, and you can only see it here after you really focus. So watch the delay between the green player applying the first input and when the cube moves. So remember that in this approach we just send our input to the server, and we display the new state after it's been physically run on the server, and we get the full response. So there is no way for us on the client to display what should happen. And that's an unacceptable delay between player input and player feedback. So for example, if you want to shoot, you want to see the gun fire immediately and not after your round trip to the server. That's unacceptable for real-time games. So here in our diagram, that would be the delay. So when the player actually presses the button till they see their input being applied, that's the round trip to the server delay time, which is totally unacceptable for real-time multiplayer games. Okay, so turn-based server authoritative cheating. Most of the cheats that were possible in client authoritative have been eliminated because there is no game logic on the client, so there is nothing to hack. Players can still use third-party AI For example, in chess, they can use stockfish to determine their moves for them. But that's the kind of cheating that's the other kind of cheating. And of course, cheating can try to access the information in the game state, because server is constantly broadcasting game state to all the clients. So some wall hacks can be implemented, for example. Okay, so to sum up, turn-based server authoritative. It's called turn-based because we have to wait a full round trip time before seeing our input, and it's only good for turn-based game. It's only acceptable for turn-based games. Game rules are in a central place on the server. We have a very clear and clean input state communication, so clients just send the state and server just sends the input. However, it's unacceptable for real-time games because of this delay, and of course players with lower lag have a clear advantage in such games. So the next idea we'll be talking about is server authoritative. Basically a very similar concept in that the server will play the actual game, however will not thin out either the server nor the clients. So the basic idea is that we play the game simultaneously on all clients as well as the server, synchronizing inputs and game state. We do our best below the actual gameplay and the networking layer below to keep the game state synchronized. And that's the approach, basically state-of-the-art approach with different twists, of course, which I'll talk about in a second. State-of-the-art approach in many esports games, like for example Counter-Strike or Call of Duty Warzone. If you've ever played any of those, then you've seen a server authoritative, which with advanced algorithms, networking algorithms on in actual games. Let's take a look at our diagram, again focusing just on one player, one client, because that's gonna matter right now. We send the initial state from the server, and then the idea is basically when the player decides to apply some input. So for example here, let's move right. The client says let's move right, and we have the game logic both on the client as well as the server. So the idea is to apply the movement on the client instantly, so that we resolve the issue of high latency, of high delay between input and and state change, as well as send the message about the input to the server. So we're able to play and give feedback to the player instantly, and of course we inform the server so that the server can have the same state. So that's the basic idea, and then when the new state comes back, we can confirm that that we have the correct state. And that, ladies and gentlemen, is called prediction. We've arrived at the first important algorithm in server authoritative that's needed there to create smooth networking experience. So prediction being the idea that you predict to the future what this input will look like, and then you wait for the response from the server. So far so good. Let's introduce the other player, because it's called multiplayer, so we have many players. And here, in our multiplayer scenario, when the second player tries to actually play something and do something. So let's go through this example first. So the server sends the initial state to all players. That's pretty straightforward. And now let's say they both want to move the cube right. So they both apply the input. They can apply it locally, and as well as send that input to the server. The server gets both inputs, and is able to apply both of them. So it moves the square, instead of moving it just by one, it moves it by two steps, and it's able to send the new state. So now, so now in both client 1 and client 2, we get the state that is invalid. That is not the same as the state that we have locally. And then we have to apply, basically accept it, because that's what the server sees. And yeah, we accept it, but that's called reconciliation. We actually have to turn back time a little to reapply our previous inputs. And that algorithm is called reconciliation, and it's another key factor of creating a smooth multiplayer experience in server authoritative game. Of course, the situation is much more complex than that in a real world scenario, because clients apply inputs all the time during the gameplay. They don't wait for the response from the server before applying the next input, and both clients do that, obviously. And they constantly send their inputs, and the server constantly responds with the current game state best of their knowledge. And when the server when the server applies inputs from both players, they have to locally, when they receive it, obviously the round trip to the server is less than the frequency of gathering input, so that we have to turn back. So when we run reconciliation on client 1, for example, we have to roll back time to a few states back, and then reapply our input so that it's as smooth as possible. And let's look at a more real-world example. Again, here are a cube game with blue player on the left, and green player on the far right, and the server state in the middle. So when we run the simulation, we can see that, looking first at the middle, at the middle picture, in the middle we can see the server state. So the gameplay is totally smooth there. There is no jitter, not anything, and it's just a state from the server. So from all those inputs, applying all those inputs sent by the clients. Now focusing on the right, we have the client, the green cube client. They send their inputs and they predict their state to the future. However, when the collision happens, there's some jitter there, and that's because of reconciliation kicking in, because we were not able to predict the exact collision between players, because we were not able to predict the other player's movement. So the engine basically detected that the state is not valid and had to run reconciliation, turn back time, and reapply the green player's input on the new game state. And that you can see as a jitter during gameplay. Here you can see that you can see a slow motion movement. The ghost is the current state, and the ghost behind is the server state. So basically, right away, as the player presses their right arrow key, they started moving locally, and that's just a prediction of what will happen. And then the server catches up and starts applying the same inputs so that they get the same outcome. Of course, different things can happen depending on how deterministic your game state is. It's most physics engines, including the one in Unity, are not deterministic, and there's no way to make it deterministic. However, that's the way. That I digress. Anyway, here another example. Here we can see the parallel state from the server, from the perspective of the green player in full. So here you can see that the blue player moves, and you can see the ghost of the state. That's the same perspective as on the previous slide. So we can see the blue player's perspective locally and the server perspective as a ghost. So they're able to predict to the future what will happen, but they see the blue player with some delay, so they're not perfectly able to predict the blue player is not perfectly able to predict the instance of the collision, so that the time is rolled back and the inputs are reapplied. And here is the same collision, basically run without reconciliation. So in one ghost is local, as the collision was detected locally by the game engine, and the other one is played on the server. So without any reconciliation on the client, you can see how much of a difference there would be between those game states if there was no reconciliation there. It would become very undeterministic, and that's why reconciliation is practically necessary for real-time gameplay. At least when physics involved and when non-deterministic any kind of non-deterministic gameplay is involved. Okay, now what about lag? Of course, lag is important, and it affects our gameplay. Here we can see the comparison. On the left, we'll have 4 ticks of lag. So 4 ticks of lag, and on the right we'll be able to see the lag that's twice as big, so 8 ticks. And again, playing from the perspective of the blue player, the collision on both clients, they're visible a little differently. However, the final state is always the same. The reconciliation, you can see much bigger reconciliation in the right and some jitter on the right because of lag. However, the final game state is always the same because the state from the server is always applied, and regardless of the lag, the same inputs are being applied anyway. And of course, the other player moves as well, and we have to take that into consideration. And of course, here because the other player moves, the cubes are in slightly different positions, and it greatly affects. It's basically chosen that way. The gameplay here is chosen that way, so that my opponent's movement greatly affects my inputs as a player. The prediction is correct sometimes, most of the time, and it's able to those cubes catch on, and they end up in the exact same state. Okay. Cheating, server authoritative. Basically, we haven't changed much between server authoritative and turn-based server authoritative. The game is still being played on the server, and locally we're just able to predict what will happen, but actually what happens is determined by the server. So same cheats and basically same cheating methods could apply. It's not possible to manipulate game state because you cannot access the server directly, and you're just sending inputs, so you're immune to all kinds of cheats that are possible in client authoritative gameplays. However, you can use external programs. For example, you can exploit the fact that all game state is being sent to all the players. For example, creating wall hacks. Or you can obviously use third-party AI like aimbots, for example. So server authoritative, it simulates the game on the server while predicting the game on the clients. And when the prediction turns out wrong and turns out incorrect, it has to roll back time and do reconciliation and reapply those same inputs. So we've looked at some possible implementations of multiplayer, but they basically fall into 2 basic categories, client authoritative and server authoritative. So those 2, with client authoritative being, for example, peer-to-peer, or client authoritative with server as a relay. So in this approach, you just send the state of your game object to the server, and the server forwards it everywhere. You unfortunately have no full history of the game, and it's really difficult to solve conflicts. You have no control over players' actions. It's a really good and simple approach for casual and co-op games, where one player becomes the host. Sometimes it requires networking knowledge, even when using existing libraries that are ready to use, because sometimes you need to resolve those conflicts and decide who wins. For example, when players shoot at one another, you have to determine who shot first. And the second approach is server authoritative, which is the best possible state synchronization. It's used in all esports games worldwide. So every AAA game using some esport being competitive, esporty, possibly uses server authoritative gameplay with all those algorithms of prediction, reconciliation, lag compensation, and so on. So you basically, the difference is that the game is being played simultaneously on the server. So you have a fair game outcome. It's resistant to many forms of cheating that are there, and those exploits are available easily on client authoritative games. And implementing it requires significant know-how of those algorithms I mentioned, for example, as well as packets and connecting players, so on and so on. And for example, actually launching the game on the server. And there are unfortunately no simple, easy to use tools available up until now. Because of Olympics, which I've talked about briefly. It's our project that we've been working on for better part of past 3 years actually. And what it is, it's a tool, it's a complete package for multiplayer games, which you can download and use in your projects, taking advantage of everything that I talked about. So server authoritative gameplay with prediction, reconciliation, lag compensation out of the box, so that you can easily implement it, easily import it, and just use it in your games. So we have no netcode policy, so that you don't have to focus the same way that you don't have to, when using Unity, you don't have to worry about implementing collision detection, for example, you just use it. It's the same thing with Olympics, you just use our netcode that's doing its best behind the hood, behind the scenes to synchronize your state. It's fully server authoritative, with, as I said, prediction and reconciliation, so it's bulletproof by design, with many other features like AI-based abnormal player detection and machine learning-based matchmaking algorithm, as well as obviously seamless deployment and automatic architecture scaling and many other features. So if you want to use it, I'm thrilled to tell you that the alpha version is available. It's available right now, launched this month. So I'm super excited to invite you, and you just go to olympics.cc to learn more, and email us at hello@olympics.cc so that you can get the access to the free alpha version, which you can check out and try to import into your game. And later, of course, when we migrate to production later next year, deploy your game with us. Thank you. It's been a pleasure talking to you, and I'm happy to take questions.